Hi everyone, my name is Russ Conti. I'm the developer of a number of really cool data science packages that are posted on Crayon. In this video, we're going to be looking at one of them, NumericEnsembles, and we're going to use it to predict the price of used BMWs. This is notoriously difficult to do, but my NumericEnsembles package makes it super easy. In fact, all I had to do was just set it up, hit run, and I actually went to lunch when it did all of the model building and the validation and the graphs and the charts. It did everything that you're going to see starting in just a couple seconds. The results are amazing because the error is less than 1%. So we can get better than 99% accuracy on predicting the prices of used cars from some really interesting data. So let's take a look at this. Hopefully you're as excited as I am. Let's get this started. We're going to start by taking a look at the basic statement of the problem, which, as everybody knows, is you can never really get an honest price for a used car. And then we're going to meet the data, which is a BMW used car price data set from Kaggle.com. Thank you to the good people at Kaggle.com for making that available. Once we have the data, we need to build statistical models. So we're going to take a look at what I'm calling America's next top statistical model, at least for this data set. And once we get the conclusions and recommendations, there's a really valid question. Can you trust the conclusions that the models are telling you? In other words, can we rigorously test the results? Answer, yes. And my NumericEnsembles package will do that just fine. Thank you very much. And then we're going to wrap it up. So in terms of a statement of the problem, it's harder to get a clearer one than this. This might be the clearest statement of a problem of all time. In 2001, the Nobel Prize in Economics, I'm not kidding, this is true, was awarded to the three guys you see pictured there, George Akerlof, Michael Spence, and Joseph Stiglitz, for their work showing you can never really get an honest, fair price for a used car because they said information always favors the seller of the car, and you'll never actually get a fair price. And for this, they really did get the Nobel Prize, and that's them at the Nobel Prize ceremony holding their awards. So let's challenge that in the next couple of minutes. We have a data set of 10,781 used BMW cars, and there are only 9 features. You'll see the features in just a second, but this is the page where the original data set comes from, and I'll put a link to this in the description. So let's meet the data. And as you can see, there are just a couple of things we're looking at: the model, the year, the price, transmission, mileage, fuel type, tax, miles per gallon, and engine size. And what we're going to be modeling, obviously, is the price. And this is just the first 10 rows. As I said, it goes through more than 10,700 rows. But let's take a look at a couple of these. So as you see, this is the engine size. This is a bar chart of the engine size, and this is all done in R. I think R looks really, really good when it does this. I prefer R over something like Excel, but that's just my personal preference. I think it's clearer and easier to see, and you're going to see that in all of this. So you can see that some of the engine sizes are actually 0, and you'll see why in just a moment. It's because there's no engine in those cars. Most common engine size by far, of course, is 2. And then we're going to be able to look at a couple of other things in terms of fuel type. The majority of these are diesels. A couple of them are electric, which means if they're electric, they don't have an engine. Hybrids, others, and petrol gas. The models that we're looking at, there are a bunch of 1, 2, 3, 4, and 5 series, as well as the X series, X1 through X7, and a smattering of the others. Taxes. You can see what the taxes are on the sales, and then we can look at the various kinds of transmissions that the cars have. Some are automatic, a slightly smaller amount of manual, and then there's a semi-automatic here. I don't see that many manual cars, but it's, to me, encouraging to see this here. And then let's take a look at what year the cars were made. All the way back to 1996 up to 2020, and you can see the majority of them were made between 2016 and 2020. So one of the things my NumericEnsembles package does is it answers what may be the most useful question. Out of the features, which ones are the most important in predicting what you want to predict, in this case, the sale price. And it actually gives it to you automatically. So the most important feature is the engine size, followed by model, followed by year and mileage, and then it diminishes after that. My running kind of half joke is, these customers are looking for power. This is what most strongly predicts it, kind of like in a general sense. But here's something really, really, really cool. What you do not need to accurately predict the price of a car, you don't need the original sale price. Don't need the condition of the car. Don't need a maintenance record. Don't need a mechanics eval. Don't need the safety record of the driver. Don't need to do any internet research. Don't need to do any interviews. Nothing else is needed except the data science. So let me introduce you to my numeric ensembles package, which I set up as a team of rivals. I've always thought that a team of rivals is a whole lot better and going to give you much more useful and accurate results than a very similar guided set. So there are a total of 32 statistical models in numeric ensembles, and 18 of them are individuals, 14 are ensembles, and it's a really cool mix because some of them are regular learning, some are deep learning, some are individuals, some are ensembles, some are optimized by tuning, some by cross-validation, some not optimized, on and on and on. As you can see, this is a real team of rivals built that way intentionally. It's not just an oversight or, gosh, wouldn't this be nice? No, this is what we're looking for. And I did a lot of things to make sure that the results would be reliable. One of which is, instead of just running this once and saying, ta-da, here we are, I resampled it 25 times. And each time it resamples it, it mixes all the data up, says, okay, let's start over again, start over again, start over again. And it does all that. That helps get more accurate results. I wanted to see what it would look like if we did something called stratified sampling, which means you keep these values the same. And as you can see, for train, test, and validation, my numeric ensembles package did a phenomenal job. So what are the results? Results start here, and the most accurate results, meaning the lowest error, are at the top of the list. So the most accurate statistical models are Ensemble Cubist, Ensemble Earth, Ensemble Bayes GLM, Ensemble Neural Net, Bayes RNN, Ensemble Bayes RNN, Ensemble Lasso, Ensemble Gradient Boosted, and Ensemble Elastic. There are more, and you'll see them more in just a couple seconds. But there's a common element here. Ensembles beat individual models very often, most of the time. And if we look at it, not only does my numeric ensembles package give you the error, so for example, for Ensemble Cubist, that's 28.5225, it also gives you the lower and upper 95% confidence intervals, standard deviation, and something we're going to go into in just a minute, which is the overfitting. That's how we're going to test and challenge some of these results. Now, you might be looking at me going, hey, Russ, I thought you said there were quite a number of them. I'm seeing less than a dozen here. Where are the rest? Well, the rest of the statistical models are here. And as you can see, the results are nowhere near as good as the ones we saw a moment ago. And all the ones at the bottom of the list are individual models, not ensembles. That's why their performance is at the bottom of the list. It's not as accurate. One of the nice things that Numeric Ensembles does is it gives you a simple bar chart so you can compare all of them. The ones on the left are much more accurate. The ones on the right, like PLS and PCR, are much less accurate. They have much greater errors. But it does a couple other really cool things. Let's test and challenge these results and see the performance. You might be in this business a really, really long time. This might be the very first time you have ever seen all these models tested and then be able to compare them by each resampling. So you can see how each one of them did. Some of them, of course, are more consistent. Some of them are more up and down. And you can see how it did on every single resample. You might have done this a long time. This might be the very first time that you've actually seen this. And Numeric Ensembles gives a whole bunch of these. I'm not going to go through all of them. I just want to go through a few of them. And the one that I'm going to call as the best, and you'll see why in just a second, is something called Ensemble Earth. And this is the summary results. So you can see the predictive versus actual, residuals, histogram of residuals, and the QQ plot. Let's look at the first three of those. Here's predictive versus actual. You could be in this business an extraordinarily long time and not see predictive versus actual look this good on anything. But when you're dealing with ensembles, that's going to happen. One of the questions is, what happens to the residuals? And so I made sure that you had a plot of the residuals. You could see where the zero line is, make sure everything's good there, and also a histogram of the residuals, which is about as close to perfect as you can get. Which raises the obvious question. Can you test that? How rigorously can we test the results? And mainly, is this overfitting? So let's take a look at what overfitting actually is. Overfitting is when you put all this stuff together, which again NumericEnsembles does automatically, you're going to get an error on the training data and an error on the holdout data. And overfitting is when the error in the training data is really good, but when you actually apply it to the holdout data, to new data, it's not nearly as good. It's garbage. It's crap. And I said, hey, let's just make that into a simple ratio. I'm going to call overfitting the error of the holdout data divided by the error of the training data. And obviously you want those to be good. You want it to be closer to 1. So closer to 1 is the best you can get. So as an example, if the holdout error is 24 and the training error is 12, that gives you an overfitting of 2, as you see in the lower left. In the lower middle, obviously if they're both 12, that gives you 1. And if the holdout is 6 and the training is 12, that actually gives you underfitting. NumericEnsembles automatically gives you a bar chart with all of them, and it's the mean times all the 25 resamples, which I think is really, really cool. And as you can see on the far right, Ensemble Cubist is the bad boy in the crowd, and it's way, way, way high. So Ensemble Cubist is not going to be our final choice, even though it has a really good mark in a couple other areas. If it's overfitting, the answer is no. In fact, NumericEnsembles does a couple other things. It takes every single model, every single resample, and then plots it so you can actually see, is this really overfitting? Some of them are, some of them are not. And you can even turn this easily, and NumericEnsembles does, into a histogram. So we can see which models are overfitting, which are not, and then we can take appropriate response. It does another, NumericEnsembles does another really cool statistical test, which I'm just going to call the KS test. So if we look at the far left, it says Ensemble Earth. What the question here is, when Ensemble Earth produces a result, how likely is that to come from the original data? So it's going to compare those two, and it's going to say, hey, how similar are these? Are these likely to come from the same? And in Ensemble Earth, yeah, it's the best possible result. When you look on the far right, those do not come from the same result as the original data. So those would be ones you would not want to use. So wrapping it up, Ensemble Earth is the winner. It's got a great error rate, does really, really good on the overfitting, does really, really good with the KS test. So Ensemble Earth has the best overall score of the 32 models on the KS test. It has a mean prediction accuracy of 99.77905%, and my NumericEnsembles package automatically creates a 95% confidence interval of 48.7304 to 51.7298, which means in English that there's an average error of a little over $50 on a car with an average price of $22,000, $22,733. So that means the error is less than 0.3 of a penny per dollar. That, quite frankly, is extremely good. And as you saw, we took a look at all the overfitting, all the statistical tests, and there's more that I'm not showing you, but it does all of this. So a conclusion is this used car data set from Kaggle, the prices of the BMW vehicles can be predicted at better than 99.7% accuracy, which is, I think, amazing. And it automatically completed all this, including all the graphs, everything else, without any errors and any warnings. A couple of other things. NumericEnsembles never makes any use of or calls to any large language models, no coding assistants, no commercial software, no chat bots, none of that stuff. Everything in NumericEnsembles is completely, totally open source. The user's data is never saved, stored, sent, sold, tracked, cached, or used in any way except to build the models, and then deleted as soon as the session ends. So all the power to get these results is built into the NumericEnsembles package and then the open source packages that it uses. So, and play with it. Play with the NumericEnsembles package, and I'll put a link to when you can actually play with it with the actual BMW dataset, which is really, really, really cool, and have some fun with it. So thanks for checking the video out. Hopefully you found that really interesting. And like I said, at the end of the day, the accuracy of better than 99.7% on the holdout data is amazing. And as I said, NumericEnsembles will help you immensely in this process. Looking forward to comments and feedback. Feel free to get in touch with me if you have any questions. Thanks again for the video. Hopefully you enjoyed it. We'll see you in the next one, which is going to be about fraud. See you then. Thanks.